for overtime? Try to. Okay, so yeah, I'm going to talk to you today about some work that was done with a bunch of people at Google AI, various capacities, especially Pavel, who can't be here today, but also Josh Dillon, Ian Langmore, Dustin Tran, and Srinivas Sutpan. So, I'll start by a kind of silly rhetorical question. Which of these target distributions do you think is going to be easier for Hamiltonian Monte Carlo to sample from? This can stand as a rhetorical question. I don't want to ask anybody to actually answer it. Clearly, the ill-conditioned Gaussian on the left is harder than the perfectly conditioned Gaussian on the right. Likewise, I think I'd rather sample from something log concave than something sort of weird and banana-shaped like that, or God forbid, something heavy-tailed and weird-looking like this funnel. Which is known, which HMC is sort of, this is like our favorite pathological example for HMC. So basically the point of this talk is taking stuff, we want to take stuff that, we want to take target distributions that have shapes like the one on the right, we want to make them have shapes like the one on the left. So this is, you can think of in some sense as sort of like another perspective on the kind of approach that, that Maria was talking about this morning, but instead of using program transformations, we're going to try and do it using invertible flows and stochastic gradient. So this is, think of as an instance of this kind of transport map MCMC idea that Yusuf Marzouk's group has done some really nice work on. Basically the idea is there's, you imagine you've got some bijective map F. So our original parameters I'll call theta throughout the talk, and I'll say that z is what happens when you pull theta back through some invertible map. I could have said it the other way around, but this way is easier. So as others have noted, the change of variables formula gives us a very straightforward way of saying what is the density of z as opposed to in z space as opposed to in theta space. It just involves this determinant correction. And so, as I said, I think I'd rather sample from the thing on the right than the thing on the left. If I can tune f so that when I pull theta back through f inverse, the density of that pulled back distribution looks like a standard normal, I would much rather sample in that space than the space on the left, right? Because that's just going to be really easy and well conditioned. So that's the basic idea of transport map MCMC. Now, right, so at a high level, step one, fit this map so that we can make P of z approximately normal, run MCMC on P of z, which hopefully looks approximately normal, and then push the samples back forward through F to get samples in the space that we originally defined the model in. So that's great, but there are some key decisions that, that matter a lot in terms of how effective the strategy is going to be, and that's really kind of the point of this work, is making some of these decisions. So one question is, what form should we choose for this invertible mapping? It needs to be flexible, it needs to be bijective, and it needs to be tractable to compute the transformation and its log dev Jacobian. Then another question is, I said I want P of z to be approximately like the standard normal. If I can make it exactly that standard normal, I would, but of course then I wouldn't need MCMC anymore. So what do I mean by approximately? What's going to be sort of the right mix of getting the properties we want while also being easy to optimize. And finally, what sampler should we use? So what I'm going to be calling neural transport HMC or NeuTra-HMC. We're going to use inverse autoregressive flows trained using stochastic variational inference, and we're going to sample using Hamiltonian Monte Carlo. Why? Because SVI is fast and stable and doesn't have the sort of horrible problems that, minimizing Kale in the other direction tends to have. IFs are kind of the new hotness, although maybe neural ODEs are the new hotness, and we should think about those. HMC is really one of the only things that actually works in high-dimensional problems in any kind of reasonable amount of time. So I'll sort of go through a little more detail about sort of what we're doing in each of these cases and try and build a little bit of intuition. So variational inference, what we're going to do is try and minimize the Kale. The usual thing, we're trying to minimize the Kale divergence between Q of theta and P of theta is usually the way that we would frame this variational inference problem. An interesting thing, though, is because the KL divergence is invariant to changes of variable, the Jacobian terms just sort of cancel each other out. That's equivalent, actually, to trying to minimize the KL divergence in z-space, right? So, usually we think about trying to take Q and warp it around so that it matches this weird-shaped P thing. But we can equivalently think about the same problem as taking P and trying to warp it in the transformed space so that it looks like a standard normal, right? So this is exactly the goal that I said we were going to set out to do. And I think this is sort of an interesting complementary perspective on these variational methods that sort of, it's actually, in some sense, we usually think of kind of trying to optimize this mode-seeking distribution in data space, but that's actually equivalent to trying to optimize this mode-covering distribution in z-space. So I'm not going to spend too much time talking about the exact form here, but it's another one of these, tractably invertible transformations that involves a shift and a scale of every dimension in a way that sort of gives you this lower triangular Jacobian that makes everything nice and tractable. Every element of theta can be computed directly from Z. You don't need to, it's not dependent on you don't have to compute theta sequentially. Going the other direction is really expensive, but for variational inference, all we really need to do, for variational inference in HMC, we can actually work entirely in Z-space. And so we never actually need to pull samples back explicitly through the inverse of this transformation, and so that's not a problem. So we have everything we need to do SPI, and of course, as Will mentioned, stacking these things yields a more tractable, a more flexible family of transformations. So this is just a recipe for getting more power, which is a good thing. And then finally, Hamiltonian Monte Carlo. Probably many of you are familiar with it, but just to sort of recap, it's a sampler that uses gradient information, which is basically kind of the only thing that, gradients are kind of the best deal going in high dimensions. You get a, order D information for order 1 extra computation. So it generates proposals by simulating these Hamiltonian dynamics, where the state changes proportional to the momentum, these auxiliary momentum variables M, and the momentum just evolves according to the gradient of the log density, which we can think of as a negative energy. So HMC is great. It's known to mix very quickly on strongly log concave target distributions like normals. And it's often the only thing that works in high dimensions, but it doesn't always work. It's sensitive, it's quite sensitive to conditioning, just like SGD, or more like SGD with momentum if you tune it right. But it's not even geometrically ergodic on distributions with heavy or light tails, which is, so it can actually fail catastrophically on certain kinds of distributions. So, putting it together, HMC in the transformed space. So just one thing to note up front, if you have a halfway decent autodiff system, this is not a big deal. You can just autodiff right through the transformation too, and it just, and everything just kind of works out. Well, one other interesting thing to note, if you're familiar with this sort of class of methods called Riemannian manifold Hamiltonian Monte Carlo, is that actually doing HMC in under a nonlinear change of variables is a kind of Riemannian manifold HMC. Basically, in continuous time, pushing the Hamiltonian dynamics in Z-space forward to theta space basically gives you Hamiltonian dynamics on a Riemannian manifold whose metric is this Jacobian outer product inverse, which, is maybe not so surprising, but it's interesting, right? So, this, if you like the idea of RMHMC, but you don't like implementing it or using it, as probably some number of people in this room that describes, this is an alternative, basically, right? So the upsides are, one big one is we get to use an explicit integrator, just a good old leapfrog integrator, which is really just nice and easy to implement, and not at all finicky, unlike the implicit generalized leapfrog integrator, which you have to solve this fixed point equation, which doesn't always converge every step. We don't need to derive, implement, compute Fisher matrices, which is a hassle and needs to be done model by model. We don't need to consider prior and likelihood separately. We don't need to make sort of heuristic choices about how to incorporate prior geometry, which there are a couple sort of, the fact that there are multiple proposals out there for how to incorporate prior geometry in RMHMC is sort of suggestive. On the other hand, there's one big, arguably a downside, which is that we do need to learn the metric. So we do have to pay this upfront cost of training our bijector, and if we fail to train our bijector well, then we will pay a price for that. Whereas with RMHMC, there's no sort of training process that could fail and that requires upfront costs. So that's sort of the trade-off, I would say. So just to give you some quick intuition, here is an example trajectory on this kind of heavy-tailed target distribution. Black dots are posterior samples to give you an idea of the shape of the distribution. The red dots are a vanilla HMC trajectory run for 200 steps. The blue dots are a transformed HMC trajectory pushed back into the original space and run for 50 steps. And things to notice are that it makes a lot more progress in a lot fewer steps. And it actually is able to sort of change its step size appropriately when it gets into a lower density region, which is exactly what you want things like RMHMC to do. So this is sort of qualitatively what we want to be happening. A few more qualitative results. Things to take away from this picture are that IAF is often able to produce a good approximation, but it can't produce a perfect approximation usually. And that the blue and black dots, which are samples from vanilla and NeuTra-HMC, are basically qualitatively similar. Actually, this funnel picture is a little misleading because those sort of darker blue dots are HMC chains that were initialized from the posterior but didn't actually converge. Or actually, didn't just not converge, or like actually not moving, they're just rejecting. So it looks like HMC is working up here, but it actually isn't. Whereas NeuTra works fine. Some more sort of kind of quantitative results, effective sample sizes. We get usually a nice speed up in terms of what is a fairly conservative number of effective samples per second. This includes the cost of back propagating through the bijector. On the funnel, basically, I mean, okay, so the way to read these is these three things on the left here, identity, diag, and trill. Those are just no preconditioning, diagonal, linear preconditioning, full rank linear preconditioning, and then preconditioning with 1, 2, or 3 IFs. And basically, what we see is, we get typically a few x to maybe a 10x speed up from learning something about the posterior geometry in this kind of initial, by fitting this, solving this variational inference problem, learning something about the global geometry of the target distribution. That's something that translates to real acceleration. So far I've talked mostly about the kind of classic full Bayes setting where you have some posterior that you want to sample from and it's just one problem, but actually this strategy plays very well in the amortized inference setting as well. Right, just where you have some inference network that's spitting out a bijective transformation for every set of latent variables. So we use this to train an MNIST-VAE decoder, and Pavel did a great job of actually getting a strong baseline there. But actually, we can see, even over this very strong baseline, we can get some nice improvements in held out log likelihood. In the interests of full disclosure, I should say, warping geometry can be dangerous, right? If you, it is possible to do more harm than good if you aren't careful. Sometimes even if you are, and sometimes even if you just use a linear transformation, which we found a little surprising. So these are the worst marginals that we could find on this sparse logistic regression problem, and with different kinds of preconditioning. So these are marginal density plots, log density plots. This This is on a log scale, that's very important. There really is not very much mass out in these tails, but there is some. And what happens is if you use a weak preconditioner, then everything works fine. If you use even an affine, a full rank affine preconditioner, what can happen is it winds up essentially shrinking the step size way out in this tail because it didn't sample in that region. Sort of Tom's point from earlier about exploration and exploitation. If it's never seen samples there, then it may not optimize ideally for there. And likewise, when you use these IAFs sometimes, it makes it just a little bit hard for the sampler to actually get all the way out into these tails that don't have very much mass. Solving this in general, I think, may be challenging. Is a little bit of a chicken and egg problem, right? That we don't know if there's mass out there if we never sample out there, and so I think some of the issues that Tom raised earlier, I think, are very relevant here. And finally, a word on relative costs. So fitting this IAF is not free. You might ask, when is it worth it versus just like running your sampler for longer? So I would say there are a few considerations. One is if you're drawing lots of samples, like you want to estimate a credible interval, and that requires a lot of samples. If you're doing amortized inference, then in some sense this is sort of free. And if there's lots of data, you can get cheap unbiased gradients by data subsampling. Then again, it will be probably relatively cheap to solve your variational problem. Basically, anytime that variational inference is cheap relative to MCMC, variational inference is going to be cheap relative to MCMC. I guess one other thing that's not on here that I forgot to put on the slide is if you are trying to sample from some distribution that's really hard for HMC that has geometry that one of these flows can correct, like the funnel. So to summarize, NeuTra uses modern variational inference techniques to speed up HMC, or if you want to think about it the other way, if you have some variational approximation and you want to improve it using MCMC, then this is a good way to do that. Offers many of the advantages of RMHMC, Riemannian HMC with fewer drawbacks, in my opinion. But be careful. MCMC diagnostics are kind of, it's a little bit of an art. It works in sort of both this classic full base setting and this amortized inference related variable setting. And finally, I'll just say all the pieces you need to implement it are in our library TensorFlow probability. All the sort of bijectors and MCMC libraries and autodiff and all that stuff is, we have some good primitives for doing this sort of thing. So that's it. Thanks a lot.
Time for one or two questions.
It's another chicken and egg problem as well. We use HMC in order to get some good mixing or to explore the posterior really very richly. But in order to train the IF model, we already expect to have explored posterior quite well in order to get the benefit. So, for several models, say you deep learning model, deep learning model, right? These are something to challenge and how does it help?
Yeah, so, posteriors for Bayesian neural networks, I don't think anybody's really cracked that. And this is not, this is a solution to slow mixing, but it's not a solution to bad search, I would say. I think if you think about it from the perspective of taking a variational approximation that's maybe under-dispersed and improving it, I'm happy to claim that this will improve on a bad variational approximation, and that I've written at least one other paper about that sort of perspective of like running a sampler for a little while, initialize from variational distribution. There are situations where that's a useful thing to do, and I think if you're going to do that, then you should do it this way. But yeah, I mean, in general, like if you're trying to sample from multimodal posteriors, that's a global search problem, and global search problems are hard, and you have to solve them with global search methods, and this is not a global search method. Thanks.
Well, we could answer one more question, I guess. Or well, okay. Or we move on.